Right. There we go. Can you see my slide that says oxidation number? Okay, perfect. Well, let's review what oxidation number was, okay? And oxidation number is just a way for us to determine the charge that an atom would have in a molecule or an ionic compound if the electrons were completely transferred. Okay, so say we look at something like, I think we looked at the nitrate ion the other night, NO3 minus, right? What's the charge of the nitrogen in nitrate? What's the charge of the oxygen in nitrate? And if we look at these rules, it's going to help us to be able to solve or answer that question. The first rule is the second rule says free elements in their uncombined state have an oxidation number of 0. So if you have just plain old sodium, beryllium, whatever, hydrogen, oxygen, phosphorus, if you have, just plain old carbon, just plain old magnesium, right? They all have an oxidation number of 0. Sorry, that's my brother calling me. Can you still see my screen? Sorry about that. Okay, good. I'll text him and say. Okay, there we go. So again, a free element, just like it is on the periodic table, has no charge. Okay, it says here that if you have a monatomic ion, the oxidation number is equal to the charge. So if you have lithium with a positive charge, it's got +1. If you have lithium with a iron with a 3+ charge, its oxidation number is +3. If you have O2 minus, it's going to have a -2 charge, so on and so forth. This next one says the oxidation number of oxygen is usually 2. There's very few exceptions to that, and I mean very, very few. One of them would be hydrogen peroxide, where the oxidation number, it's -1, and then O2, I don't know why it's there, because in O2, the oxidation number is 0, which is shown up here, so that's an error. We can even just scratch that out. Okay, we'll just get rid of that. Oops. The next one says the oxidation number of hydrogen is always +1, except when it's bonded to metals and binary compounds. In these cases, its oxidation number is -1. Let me give you an example here for rule number 4. Rule number 4. So if you have a compound like water, okay, well, if you go back a couple of rules, it said that the oxidation number of oxygen is almost always -2. Right, so if I have -2, I've got to have a total of +2 over here to balance out that -2. Well, if I have 2 hydrogens, +2 divided by 2 gives me +1. So each one of those hydrogens is +1. So there's an example where hydrogen is +1. And if you're wondering, well, can you give me an example where hydrogen is -1? Sure, I can. If you have, where is it here? Metals and binary compounds. So if you have this compound here, sodium hydride. Okay, so now the hydrogen is bound to sodium, or it's combined with sodium, and sodium is a metal. Okay, and hydrogen is not a metal. And so here, the charge of hydrogen is -1, and the charge of sodium is +1. Rule number 5 says group 1A metals are +1, group 2A metals are +2. Fluorine is always -1. It's kind of a good one because it's such a big rule, it covers so many elements, lithium, beryllium, sodium, magnesium, so on and so forth. Number 6, the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or ion. That's how I solved this problem up here. That's how I determined what the charge on the hydrogen was. I said, well, if the oxygen is -2 and the whole thing is 0, then I've got to have +2 to balance that out. And the last one says oxidation numbers do not have to be integers. They can be a half. For example, oxygen can be -1/2 if it's in the superoxide, so it's O2 -1. So each oxygen bears a charge of -1/2. Anyhow, we won't look at a ton of superoxides. Well, with that in mind, we already looked at lithium oxide, and I will just quickly erase this, and we'll go over lithium oxide again. Lithium is in group 1A, so lithium has a charge of +1, and we said the oxygen is almost always -2 in a compound. So there we go, 2- for oxygen, like that. Let's look at the next one, which is nitric acid, HNO3. Well, the first rule is that the hydrogen is not combined with any metals, and so the hydrogen must have a +1 charge. So we've already got the hydrogen complete. Now we've got to analyze the nitrate ion, NO3 minus. Well, if you remember in our rules, it didn't say anything about nitrogen, but it said that oxygen is almost always -2. So if each one of those oxygens, if each one of these oxygens is -2, and there's 3 of them, that gives me a charge of -6. Now, overall, I need to have a charge of -1. So what plus -6 gives me -1? Who could tell me? Not a trick question. Go back to my chat here. Yeah, so Chris says 5, Tyler says 5. Yeah, the answer is +5. And so my nitrogen must have a +5 charge, like that. Again, I'll prove it to you. -6 + 5 equals -1. Okay? And so therefore, my nitrogen must be 3- charge, and my oxygen must be a 2- charge. And these are the answers for the 3 elements here. So there we go, like that. The last one is the dichromate ion. You have to know this one. I'll just write it out for you if you've forgotten it. Dichromate. Okay, who could tell me if they have an idea what the oxidation number of the oxygen would be in dichromate? Should be O what? Based on the rules that we learned. What's the oxidation number of oxygen most of the time? Very few exceptions. -2, yeah, absolutely. If you go back here, it says right here in the rules, okay? Where was it? Right here. The oxidation number of oxygen is usually -2. Right there. Very few exceptions to that. So let's use that, okay? -2, okay? So the oxygen has a charge of -2 or 2-. Now, how many oxygens are there? Right? There are 7 of them. So if we take -2 times 7, we get -14, okay? The people who are putting in 14, that's the overall charge. That's not the oxidation state of the oxygen atoms, okay? So we have an overall charge of -14 from all of the oxygens. There's 7 of them, though, right? Each one has a charge of 2-, and that's the oxidation number. Now, what plus -14 gives me -2? And the answer is 12. If I take -14 and I add 12 to it, I get -2. And that's the charge of my dichromate ion. So that means that the chromium overall has to have a charge of +12. But how many chromium atoms are there? There's 2 of them. So that means that each of them must be +6. So there's my answer. My oxygen is 2-, and my chromium is 6+. Give me a thumbs up if that makes more sense, now that you've had a chance to see me work through it a little bit. Good, okay? All right, so that's oxidation state, okay? Oxidation numbers of elements in these different compounds and in this ion. There we go. And you can see that when we're talking about group 1A metals, right? Group 1A elements, that your charges are always +1. In group 2A, the charge is always +2. Once you get into the transition metals, it gets a little bit trickier, right? This is transition metals. And a lot of those can have more than one oxidation number. For example, copper, let's just pick one at random. Copper can be +2 or +1, whereas iron can be +3 or +2. There are 3 exceptions in the transition metals that can only have 1 charge. I know that over here they show you a couple others that can only have 1 charge, but the 3 exceptions you have to know are zinc, cadmium, and silver. So silver always has a charge of +1, zinc always has a charge of +2 or 2+, and cadmium always has a charge of +2. These are exceptions. You must know. You have to know these exceptions, okay? All right. Once you get over into the P block here, you can see that fluorine always has a charge of -1. But you see a lot of these nonmetals can take on all kinds of different oxidation states, okay? And some of them can take on even more oxidation states than are shown here. For example, carbon can be -4, -3, -2, -1, 0, 1, 2, 3, 4. They take on many oxidation states or oxidation numbers. All right, there we go. Well, let's keep moving on. And now we're switching gears almost, not entirely, but almost entirely. And we're going to talk the rest of this lecture about solution stoichiometry. The entire rest of this class will be devoted to solution stoichiometry. It says here that the concentration of a solution is the amount of solute present in a given quantity of solvent or solution. Now remember, when we have a solution, we have what? We have solute and solvent in the solution. The solute is what's present in a lesser amount, or a lesser amount, and the solvent is what's present in a greater amount. An example would be if you make Kool-Aid at home. Okay, you take some kind of glass or something like this, and it's got water in it, and then you put the Kool-Aid crystals in it, and then it turns this delicious red drink or whatever. Well, if you make the Kool-Aid really dilute, all right, we'd say, oh, the concentration, it's not concentrated enough, it doesn't taste good. But then we add more Kool-Aid to it, more crystals, and you're like, oh, this is delicious, it's more concentrated. Oh, it's the concentration is good. And then you could add even more. It's hard for me to do it with my pen here, but you could add too much, maybe so much. Maybe you add so much Kool-Aid that you end up with some solid. Maybe you'll have to use a different. You actually end up with some solid bits in the bottom. You're like, oh, this could rot your teeth after one sip. That's too concentrated. So we are used to using the word concentration in our everyday life to describe the stoichiometry of solutions. Now, in chemistry class, you have to know this formula, that concentration of a solution is measured in molarity. So the concentration, okay, measured in molarity. And the formula for molarity, which we use big M to represent, is the number of moles of the solute, which again is present in a lesser quantity, divided by the number of liters of solution. So I like to write this formula like this. I say that M is equal to N over V. So N stands for number of moles, same thing, and V, you can guess, stands for volume. So M, big M, molarity, is equal to N over V. It's the exact same thing as the equation that's on top. And that's how we measure concentration. It says here how to measure how to prepare a solution of known concentration. So you have a solute, and in your book it's saying you would weigh it out and then pour it into a volumetric flask, okay? Well, you should never do this, okay? This is a big time no-no, because I told you that a volumetric flask is only used for measuring volumes of liquids. It is not used for pouring solids into, never into a volumetric flask. And so you're going to appreciate my Drake meme here that I threw up, okay? When they tell you to pour a solid into a volumetric flask like this, that's a no, okay? That's a big time no-no. What you should do, the proper technique, is shown over here on this side. You see Drake being like, yeah, that's right. What you would actually do is you take your solute, weigh it out on a bounce, then you would pre-mix it in a beaker with a small amount of the solvent, and that way you can heat it up and you can crush it. You could sonicate it, which is just a way of pulverizing solids, because you're not supposed to heat volumetric glassware, okay? Do not heat. Okay, and you can use a beaker to help you warm up a solution to try to get the solvent to go into that solution, and then you would transfer it into the flask and you would rinse it in there with distilled water and make your solution like that. Okay, all right, well, that's the proper way to make a solution. Let's talk a little bit more about solutions and talk about the stoichiometry, the math behind solutions. It says here how many grams of potassium dichromate are required to prepare a 250 milliliter solution whose concentration is 2.16 molar. Big M, well, I want to remind you that big M stands for the number of moles divided by volume. Okay, well, we know what? We know, let me get a different color here. We know the molarity, that's given to us right here. We know the volume, which is given to us right here. we could rearrange this formula. We could rewrite it as M is equal to M times V, and that would give us the number of moles of potassium dichromate. Do you see the end of the rainbow now? Do you see the light at the end of the tunnel? If you had the number of moles of potassium dichromate, okay, all you'd have to do is multiply that by the molar mass, and you would have the number of grams. Give me a thumbs up if you just follow me with the rationale. Just the rationale. We haven't done the solution yet. We're going to get there. Okay. And just to put this bug in your ear, I know you're all busy people. I'm busy too. But if I can make a recommendation, would be to always give these problems the old college try. Give them a try before you come to class. Okay, so let's get started here. And the first thing I'll do is I'll give you the molecular weight of potassium dichromate. I went and figured it out. It's 294.185 grams per mole. That's way more significant figures than I need, but what the heck? This is the land of the free. So let's keep moving. Another thing, I hate it when they do this, 250. Let's put a decimal here so that we have 3 sig figs here and 3 sig figs here. All right, well, with that in mind, let's take our equation and we'll say the number of moles of potassium dichromate is equal to the molarity, 2.16 moles per liter multiplied by the volume. Can you guys convert 250 milliliters into liters in your head? I hope so. Okay, you could put here 250 milliliters multiplied by 1,000 milliliters in 1 liter, like that. Okay, and that would give you what? 0.250 liters, like that. Okay, well, if we finish this calculation, we end up with the number of moles of potassium dichromate. Let's do it. Okay, so 2.16 times 0.25, and I end up with 0.540 moles of potassium dichromate. Cr2O7, like that. Now to figure out the number of grams of potassium dichromate, what do I have to do? I'm going to take 0.540 moles of potassium dichromate, and I'm going to multiply it by 294.185 grams of potassium dichromate in 1 mole of potassium dichromate. Look at this. The number of moles of potassium dichromate cancel out, and we're left over with 159 grams of potassium dichromate. Okay, that seems perfectly reasonable to me. There is another way to solve this problem, though. Let me show you what I would have done if it was just me solving it by myself. It's that I like to do everything using what? Dimensional analysis. And so I think an even easier way to solve this problem would be to do this. Okay, would be to write the whole thing out in one fell swoop. It would be to say, okay, well, I've got 0.250 liters of my solution, and I multiply that by 2.16 moles of potassium dichromate in 1 liter. Then I multiply that out by 294.185 grams of potassium dichromate in 1 mole of potassium dichromate. Like that. Look at this. Is this magic or what? Liters cancel out, moles of potassium dichromate cancel out, and we end up with the exact same thing. We end up with 159 grams of potassium dichromate. Beautiful, huh? Now, I'm not the kind of instructor that likes to solve the same problem multiple different ways, multiple different, that's redundant, multiple ways. But every once in a while, I just like to show my students that if you need to work the problem out step by step, where first you do step 1, right? Then you do step 2. That's fine. I'd say that's totally fine. I think that this is probably a more elegant way of doing it, to do the whole thing in one shot. But either way works. As long as you get the correct answer, this beyond is going to be a happy camper, and so will you, right? It's not just about me, more about you being happy with your grade. All right, well, let's take a look at another problem. It says here, in a biochemical assay, a chemist needs to add 3.81 grams of glucose to a reaction mixture. Calculate the volume in milliliters of a 2.53 molar glucose solution she should use for the addition? Well, no matter what, we've got to end up with milliliters, right? We've got to end up with milliliters of solution. That's what the question's asking us for. It says calculate the volume in milliliters, okay? So that's where we're going. And we know that we're starting out with 3.81 grams of glucose. And we have a solution of glucose that's 2.3 moles per liter. Okay, so these are the conversion factors we got. We've got this one where we got moles to liter, and then we've been given that we've got 3.81 grams of glucose. I'm going to see if any of my students are just way ahead of me. Not way ahead, but maybe a step ahead of me. Does anybody realize what the other conversion factor that's required that's not here is? There's one more conversion factor that you need to solve this problem. Goes back to something that we've done many, many times. Yeah, grams to mole, right? We need the molar mass of glucose. Think about it. We've got grams here and we've got moles here. What's the connection? We're going to need the molar mass of glucose. And so I've gone ahead and looked up the molar mass of glucose, and it is 180 grams per mole, 3 sig figs, like that. Okay, well, with that in mind, let's see if we can figure this problem out. Okay, we're starting out with 3.81 grams of glucose, and I want to convert that into moles, but I know that in 1 mole of glucose, I've got 180 grams of glucose, like that. Look at this. Oops. Let's try it again. I've started with 3.81 grams of glucose, and I know that in every 1 mole of glucose, I have 180 grams of glucose. I see that my grams of glucose cancel out. Now I can use the concentration of my solution, which is 2.53 moles of glucose in 1 liter of glucose, like that. It's just asking us to give the answer in milliliters, and if I was to stop here, I'd have the answer in liters. And so I'm going to need one more conversion factor, and that is in 1 liter, there's 1,000 milliliters. And let's try punching that spinach into our calculator. 3.81 divided by 180 divided by 2.53. Bingo, bango, bongo. Multiplied by 1,000. And you end up with 8.37 because you should have 3 significant figures. 8.37 milliliters of solution. So this again is 3 sig figs. So if you think about what's going on here, is anybody besides me like orange juice from concentrate? In Canada, that's all we can afford because the real American orange juice, we don't grow oranges in Canada. So orange juice in Canada is really expensive. Has anybody here ever made orange juice from concentrate from the can? Oh man, no answers, just me. Okay. Oh, Chris has. Okay, 2 of us have. Anyhow, yeah, where I grew up in Nova Scotia, we couldn't afford the real orange juice. It's so expensive. You get it at a restaurant maybe once in a while. Anyhow, so what do you do when you get that concentrated orange juice from the grocery store? You pour it in a pitcher or something, and then you dilute it with water. Well, how much water do you dilute it with to make the proper tasting orange juice? That's the exact same thing that's going on here, right? The chemist wants to add this much glucose to a reaction mixture, but she only has it in a solution. So she just needs to figure out, well, how much of that solution do I need to throw in that's going to be equivalent to 3.81 grams? So you see why you always have to have this conversion factor here to get from the number of grams to the number of moles, right? This is the key step in getting from our mass of glucose and being able to use our concentration of glucose in our solution. All right? Give me a thumbs up if you think you can do that problem. Even if you're half the way there. Think, weekend's coming up, I'm going to study then. Study hard the night before. No, you'll study every day. Good. Okay. All righty. Well, let's move on and take a look at another concept. And the concept is dilution. I was in a lab just before I came here, and was talking to one of my buddies, and he said, you know, the classic joke in chemistry, the solution to pollution is what? Dilution, right? You just make it more dilute. Anyhow, it says here that dilution is taking orange juice from the grocery store, pouring it into a pitcher, and diluting it with water, right? Dilution is the procedure of what? Preparing a less concentrated solution from a more concentrated solution. Nothing more than that. And so you can see here we have a certain number of particles of our solute. Okay, and then as we add solvent, does the number of particles change? No, it's the same number of particles. And we should write that in here. Same number of particles. The only thing that changed was the space in between the particles. You can see how the particles are all really tightly packed here, right? They're very close to each other. Well, wow, over here, there's all kinds of space around those particles, right? And that's because they're more dilute. All right. Now, there's a formula that we can use to calculate the molarity or the volume of a solution when we're comparing it to a diluted solution or a more concentrated solution. And that is this formula here. It's one of the favorites of all general chemistry students. It's M1V1 is equal to M2V2. Here they say MI, so M initial times volume initial is equal to final molarity multiplied by final volume. Again, I'm telling you right now that a lot of my students just like to write M1V1 is equal to M2V2. I teach this same formula in the nursing class sometime, and in their textbook they call it they call it C1V1 is equal to C2V2, and the C stands for concentration, okay? But you guys know that M stands for molarity, which is concentration. It's concentration in the number of moles per liter. I like M1V1 is equal to M2V2 a little bit more because it's specific. It's talking about molarity, where concentration could have many different units outside of molarity. All right, well, with that in mind, let's give it a try here. Here's a classic problem that a chemist might run into in the lab. He goes to the cupboard and sees that they only have this concentrated solution of sulfuric acid. But the question is, how would you prepare half a liter, and I'm going to add a sig fig here, 500 with a decimal, milliliters of a 1.75 molar sulfuric acid solution, starting with 8.61 or an 8.61 molar stock solution? Well, this is a dilution problem, right? We're just taking something that's concentrated. Okay, this is concentrated, and we want to make something that's more dilute. And this is the volume that we want to make of this dilute solution, right? We want it to be this concentration, and we want that much. And so we're going to use M1V1 is equal to M2V2. Again, we already know M2 and V2, right? We know that M2 is going to be equal to 1.75 molar. We know that V2 is going to be equal to 500 milliliters. We know that M1 is equal to 8.61 molar. We do not know V1. Okay, and so we have to solve for V1. And to do that, we're going to say V1 is equal to M2 times V2 divided by M1. So V1 is going to be equal to 1.75 molar multiplied by V2, which is 500 milliliters, divided by M1, which is 8.61 molar. Looky, looky. Molar and molar cancel out together like that. And we're going to end up with our volume in milliliters. And when we do that, let me give it a try here. 1.75 times 500 divided by 8.61. And you need to take out 102. So it says 101.6, 2 something milliliters. But I should only have 3 sig figs, and so that equals 102 milliliters of the stock solution, right? It says here stock solution. Okay. Another thing I'll add about this problem before we move on is that I had a student ask me one time, they said, how come you didn't convert the milliliters into liters? Well, it doesn't matter. I don't have to do that because both the molarities cancel out. And so the volume could be in whatever metric unit you want it to be, and you're going to end up with that unit. So since I left it in milliliters, I end up with milliliters like that. All right, give me a thumbs up if you think you could do a dilution problem. Use this good old formula. M1V1 is equal to M2V2. Yeah, real chestnut, okay? All chemistry students have to know how to use M1V1 is equal to M2V2. Okay, the next concept is that of gravimetric analysis. I don't know if I've ever done this in my life except for when I was a student, maybe in the lab. I've never done it as a chemist when I was in industry. It's just an interesting way to determine the amount of an unknown ion, and that's what it says down here at the bottom, right? It says determine the amount of an unknown ion. So you have some kind of unknown ion. How do you identify that and the amount, or sorry, how do you determine the amount of that unknown ion? First, you do this, you dissolve the unknown substance in water, and then you react with a known substance to form a precipitate. You filter off the precipitate, right? That's what's being done here. Maybe I should have said here, the first step is you dissolve it in water, then you do the reaction, then you filter off the precipitate, you dry it, and then after that, in the next picture, they should have had a balance, okay, with a reading on it, and then you weigh the sample. So we'll say here they get some kind of weighing dish, and then you weigh the sample, and it has something in grams on it, okay, and then you use the chemical formula and mass of the precipitate to determine the amount of the unknown ion. And that amount might give you a clue as to what the ion is. Anyhow, let's give a look at a problem here. It says if you have 0.5662 grams of an ionic compound containing chloride ions, right? And you should know what chloride ions are. They're Cl minus ions. And an unknown metal. Hey, there's our metal of interest, okay? So some kind of metal, we'll call it M maybe, is dissolved in water. So you have something MCl, and you don't know what the charge is or anything like that. So it might be MCl2. I don't know. Anyhow, maybe I should delete that to not confuse anyone. Anyhow, you dissolve all of that in water, and then you treat it with excess silver nitrate. And then you're going to get silver chloride as a white precipitate. And it says here that you get 1.0882 grams of silver chloride. What's the percent by mass of chlorine in the original sample? Well, if you think about this, this goes way back to early on in this class, right? We looked at how to calculate percent by mass of chlorine, right? And you should know that the percent by mass of chlorine is going to equal to the mass of chlorine divided by 0.5662 grams of our sample, right? And then multiply by 100%, and that's going to give you the percent mass of chlorine, okay? So the question then becomes, well, okay, good, that's fine, but what the heck is the mass of the chlorine? Well, let's switch gears again. We know that we have 1.0882 grams of silver chloride. Well, you reacted it with silver nitrate. I don't know what that's supposed to be. You know, AgCl. There we go. You reacted with silver nitrate. So where did this silver come from in your silver chloride? It all came from the silver nitrate. Where did this chlorine come from? It all came from the chloride ions that were combined with the unknown metal, right? And so as long as we can figure out the mass of chlorine in the silver chloride, we're going to know what the mass of chlorine to put in our numerator here is. Okay, how are we going to figure that out? We're going to multiply the mass of chlorine by the percent mass of chlorine. Sorry, we're going to multiply the mass of silver chloride by the percent mass of chlorine in silver chloride. And so we take that, okay, and we're going to find the percent. Let me switch colors here again. First, we're going to find the percent mass of chlorine in silver chloride. It's going to be equal to 35.45 grams per mole. That's for my chlorine, right? For Cl, divided by 143.4 grams per mole for my silver chloride. Okay, then I multiply that by 100%, okay, and that's going to give me the percent by mass of chlorine and silver chloride. So I've already gone ahead and done that, and you end up with 24.72%. Okay. Now, if I want to figure out what the mass of chlorine is in the silver chloride, I'm just going to take that and I'm going to multiply this mass by 0. Maybe I should do it like this: 24.72% out of 100%, like that. And then I end up with 0.2690 grams of chlorine. There we go. There's the mass of chlorine that we started with. Okay. So now I can put 0.2690 grams of chlorine divided by 0.5662 grams. Multiply that by 100%, and you end up with 47.51% chlorine in the original unknown compound. Done. All right. So you see how I kind of worked forward? I went from here to determining what the formula was for percent mass of chlorine in this ionic compound. Then I figured out how much silver chloride that's given to me in the problem. Then I figured out the percent mass of chlorine, okay? And I multiplied that by the mass of the silver chloride that I had. That gave me the total mass of chlorine that I had to begin with, right? And there we go. I divide that, I divide that by the mass of the sample, and there we have it. That's the percent mass of chlorine in the original sample. All right. Well, with that in mind, let's move on to our last topic, I think. Yes, the last topic, which is a big one. Okay, so strap your skates on, Gordy, and we'll give this one a try. It's titrations. Who would like to take a, 5-minute break? I need a drink of water really bad. Okay, Shay says yes. I say yes. Mob rules. We win. Okay. What did Tyler say? Okay, people are saying good. Yeah, just 5 minutes. I'm parched. I had a lab this morning. I had a lab this morning, and I did a lot of talking. So just give me a few minutes here, and then we'll get back to it. All right, well, that was close to 5 minutes for sure. All righty, where were we? You guys ready to tackle titrations? Who's ready? Who's ready to tackle titration? Anyone? Game on. All right, let's do it. Oh, pop the cork. Yes. You know, titrations, again, simple math, just multiplication, division, nothing more than that. It's the concept that is difficult for students sometimes. Let me distill it for you in the simplest possible bits I can. Okay? Let's say somebody on the street gives you, a sample of an acid. Why would somebody do that? I don't know. Anyhow, somebody gives you some sulfuric acid or some HCl, and they give it to you and they say, I don't know the concentration. Okay, so somebody on the street, it's just like it's your birthday, and they gave you a bottle or something with some hydrochloric acid in it, but you don't know what's the concentration. Okay, what's the concentration of this HCl? What you can do is you can use a base with a concentration that you know. So let's say you have a sample at home, you have another jar, okay, and it's got some sodium hydroxide in it, and you know the concentration is, 1.0000 molar, okay, like that. Well, you're like, well, how am I going to use my base of known concentration to determine the concentration of my HCl? Well, remember that the concentration of your HCl is nothing more than the number of moles divided by the volume. If you took out a sample of this HCl and measured the volume accurately, you would know the volume, right? So then all you would need to know is, well, how many moles of HCl are in that sample that I took out, right? Like you took, this is a human hand, right? You took out a sample, of so many milliliters. You got the N or the V, so all you need to know is the N. And if you're wondering, where the heck would I get the number of moles from? Well, hold on. What if you did a reaction between HCl plus sodium hydroxide? What do you get? That's a neutralization reaction. You would end up with a salt, NaCl, and H2O. And you know that when this reaction is completely done, when all of the HCl has been neutralized completely by sodium hydroxide, okay, if you could figure out exactly when these are perfectly equal, when these are in a perfect 1-to-1 ratio, right? If you could know that, then you'd know that the number of moles of this is going to be equal to the number of moles of this, because the ratio is 1-to-1, right, from the stoichiometric coefficient. So based off of the number of moles of sodium hydroxide that you added, you would know the number of moles of HCl, and then you would plug that in here as the N into your formula. Now you might be, if you're not quite with me, you might be wondering, well, where would I get the number of moles of sodium hydroxide? Remember, you know the concentration of that sodium hydroxide, and you're going to know the volume that you're going to measure out using a burette. Okay, give me a thumbs up if you just follow me on the concept of titration. Nothing more than the concept. It's just a matter of figuring out when you've added the exact same amount of acid to neutralize all the base, calculating the number of moles, assuming that's the same as the number of moles of acid, and you know the volume of the acid, boom, there you go. You can figure out the concentration. Well, let's look at the definition here. It says that in a titration, a solution of accurately known concentration is added gradually using a burette to another solution of unknown concentration until the chemical reaction between the two is complete. When you hit what's called the equivalence point, it's the point at which the reaction is complete. Then it says here that you have an indicator, and that indicator is some other kind of chemical that changes color at or near the equivalence point. Okay? And so what you would do is you would set up your volume of acid in here. Okay, I'm just using this as an example. You'd have the volume of your acid in here, right? You'd have a base in the burette. You'd add a known volume of the base. You'd watch this with your eyeball. And then when it turns pink, you know that you're at the equivalence point. At this point, the number of moles of your base and I'm just using sodium hydroxide and HCl as an example, is going to be equal to the number of moles of HCl. So in order to figure out the concentration of your HCl, you already know the number of moles of HCl, right? That's right here. And the volume of HCl, you measured that out when you put it in the Erlenmeyer flask in the first place. Done. Okay, that is how a titration is done. It says here that titrations can be used in the analysis of acid-base reactions. Probably most of the examples that we'll see in this class will be acid-base reactions because we've studied acid-base reactions. We've talked about neutralization reactions. In fact, we could even write that in here in parentheses. We'll put here neutralization reactions, like that, okay? But it can also be used in redox reactions. Now, this is something that in order to balance this equation, you're like, what? How would I balance that? You'll learn, we'll put here, learn to balance redox in Gen Chem 2. So that would be Chemistry 112 at PPCC, okay? Now, even though you don't have to know how to balance these types of reactions, we can still use a balanced equation to determine the concentration of an ion based off of this balanced equation. And I think I have an example of that in here in my slides. So I digress. Let's go back to an example here. We've already read this one. You're like, what's KHP? Okay. I'll tell you in a second here. So it says here that in a titration experiment, a student finds that 23.48 milliliters of the sodium hydroxide solution are required to neutralize 0.5468 grams of KHP. What is the concentration or the molarity of the sodium hydroxide solution? Well, what are we looking for? We're looking for the concentration of sodium hydroxide. And the concentration of sodium hydroxide is going to be equal to the number of moles of sodium hydroxide divided by the volume of sodium hydroxide. Well, the good news is that we've already got the volume of sodium hydroxide in milliliters. We can convert that into liters by dividing by 1,000 milliliters per liter. And then we would end up with 0.02348 liters in our denominator. And so the question then becomes, what's the number of moles of sodium hydroxide? Okay, give me a thumbs up if you just follow me that far. All we're trying to figure out is what the number of moles of sodium hydroxide is, plug it into this formula, and then boom, we're done. Okay, well, let me help you out with this KHP thing. There's not enough information in here. KHP stands for potassium, hydrogen. Ready for this one? The phthalate. Okay, potassium hydrogen phthalate. It's an acid. Okay, it's not a strong acid, but we'll put here it's a weak acid. So it's going to react with the sodium hydroxide, which is a base. Okay, and I've gone ahead and looked up the molecular weight, the molar mass of potassium hydrogen phthalate, and it's 204.2 grams per mole, like that. Now, what we're assuming is that when we take sodium hydroxide and we react it with KHP, the base ends up taking a proton from the weak acid, and we end up with H2O, right? And then what else are we left over? We're left over with sodium and Kp, because the hydrogen that went to the hydroxide was this one here. So I'll help you out. Again, if you're like, would I be expected to figure all this stuff out about KHP on an exam? No, okay? If it was an acid that I've taught you about, like acetic acid, yes. Okay, or HCl, yes. This KHP is something that they just put in here. Anyhow, so you end up with Na, the sodium, potassium, phthalate, okay? Like that. And you can see that these are in a 1-to-1 ratio, like that. Well, from that, if we know the number of grams of KHP and we know the molar mass of KHP, we can figure out the number of moles of KHP. And if we know the ratio of the number of moles of KHP to sodium hydroxide is 1-to-1, there you go. we're going to know the number of moles of sodium hydroxide, and our problem is going to be solved just like that. Okay, so let's figure out the number of moles of KHP. And we know that we have 0. Let me move this up just a tad here. We know that we have 0.5468 grams of KHP. And I know that I have 204.2 grams of KHP in 1 mole of KHP. From the balanced equation that I provided to you, this one right here, and this one right here, I know that for every 1 mole of KHP that's consumed, I consume 1 mole of sodium hydroxide. Right? Again, this comes from the balanced equation. Okay, let's check our units. Grams of KHP cancel out, moles of KHP cancel out, and we're left over with moles of NaOH. When you do that, you get 0.002678 moles of sodium hydroxide. Now I can plug this number into my numerator right here. Give it a shot. I have 0.002678 moles. I divide it by the number of liters, and I get a concentration of 0.1140 molar for my sodium hydroxide, and that's the concentration. All right, that's our first titration problem. Actually, is it what? Yeah, it's our first titration problem. Give me a thumbs up if you follow me on that. We picked kind of a complicated acid to discuss, but just as long as you understand the stoichiometry, you're good to go. All right, great. Great. Well, with that, let's move on and look at a couple more examples here. This is more of a classic example. In fact, I don't have the ACS final exam memorized, but I know that in years past they asked a question that was almost identical to this one. So ACS final, we'll put here ACS final what type? Okay, it's the kind of question that they asked on an ACS final. I don't remember how many years ago, maybe 2, maybe 3, maybe it was last year. I see enough final exams that I can't keep track of all of them. But here it says, how many milliliters of a 0.610 molar sodium hydroxide solution are needed to neutralize, and when it says neutralize, it means completely neutralize 20 milliliters of a 0.245 molar sulfuric acid solution. The first thing we should do here is write out a balanced equation. And I know that when I react sodium hydroxide with sulfuric acid, it's a neutralization reaction, so I'm going to get a salt plus water. What's the salt I'm going to get? I'm going to combine my sodium with sulfate to make sodium sulfate, which is Na2SO4, and I'm also going to end up combining hydroxide with hydrogen, so I'm going to end up forming water, H2O. Now this is not a balanced equation. You can see that I have 2 sodiums in sodium sulfate, but I only have 1 in sodium hydroxide, so I need a 2 here. Now I'll check my hydrogens. I have 2 hydrogens here and 2 here, and I only have 2 here, so 2 times Q gives me 4. This is a balanced equation. And so now you can see that the ratio of sodium hydroxide to sulfuric acid is not 1-to-1. It's a ratio of 2-to-1. All right, well, with that in mind, let's start and see what we can do here. We want to figure out the number of milliliters of sodium hydroxide. Remember that I told you earlier on that molarity of sodium hydroxide is equal to the number of moles of sodium hydroxide divided by the volume of sodium hydroxide. And we are wanting to solve for this. So that means that volume of NaOH is going to equal to the number of moles of NaOH divided by the concentration of NaOH, like that. Now we already know the concentration, so we can even plug that in. It's 0.610 molar sodium hydroxide. So all we have to do now is determine the number of moles of sodium hydroxide. Well, look, we have the concentration and the volume of the sulfuric acid. From that, we can figure out the number of moles of sulfuric acid, and we know the ratio of sulfuric acid to sodium hydroxide is 2 to 1. Nothing more than that. Well, let's give it the old college try here. So I have 0. I've gone ahead and calculated this in liters, so I divided that by 1,000. Give me a thumbs up if you can divide a number by 1,000 in your head. Okay, because I'm going to assume moving forward that you're able to do that. Can everybody divide by 1,000 in their head? Right, if I want to take 20.0 milliliters and divide by 1,000, I move the decimal place over 1, 2, 3, and then I end up with 0.0200 liters, like that. Okay, cool. All right, so I'm going to assume that you can divide by 1,000 and move a decimal place 3 places in your mind. So I start out with 0.0200 liters of sulfuric acid. I know the concentration of my sulfuric acid is 0.245 moles of sulfuric acid in 1 liter of sulfuric acid. And from my balanced equation, I know that for every 1 mole of sulfuric acid that gets consumed, I consume 2 moles of sodium hydroxide. Looky, looky. My volume of sulfuric acid cancels, my moles of sulfuric acid cancels, and I'm left over with the number of moles of sodium hydroxide. Now, I haven't done it, but let's see here. I take 0.02 multiplied by 0.245 times 2. And I should have 3 sig figs in my answer, and it's 0.00980 moles of NaOH. Okay, now what can I do with that? I can take this, I can copy it, I can paste it into here, into my numerator, like that. There we go. So I take that number, I divide it by 0.610, and I end up with my my volume, in liters. So I end up with 0.0161 liters. Could we convert that into milliliters? You'd multiply by 1,000 milliliters in 1 liter, and you'd end up with 16.1 liters of sodium hydroxide. And that's your typical type of titration problem. Nothing more than that. Give me a thumbs up if you think you can do that one. I promise I put a question like this on your practice exam too. And I've also worked some out that I provided the solutions for on D2L. So be sure to take a look at those. Last night I was in the lab with some students and I asked them, I said, are you trying the problems that I provided the solutions for? And could you read my writing? And they said, yes, we can read your writing. And we started going over them. So be sure to take a look at those. I spent a lot of time working on those solutions. So make sure you try all those. Here's another one. I'm going to go over this one a little bit quicker since we've already gone over a couple of them. This is the last one. This one involves a redox titration. Again, let me repeat that you do not have to know how to balance a redox equation. You're going to learn that if you take general chemistry 2. We do a whole, probably half an hour on just learning how to balance redox equations. There's ways to do it in acid. There's ways to do it in base. So don't, stress about having or being able to do this. In fact, another thing about balancing redox equations is that you leave out spectator ions. Because if you read the question, it says you start with a 16.42 milliliter volume of 0.1327 molar potassium permanganate solution is needed to oxidize 25.00 mils of iron 2 sulfate solution in an acidic medium. What's the concentration of iron? What's the concentration of iron 2 sulfate? What's going on here? Yeah, what's the concentration of iron 2 sulfate solution in molarity? Here's the net ionic equation. So there's a few things you've got to be able to do here. You've got to know that in FeSO4, you've got to know that that's iron 2 plus. Now, if you're wondering, how did you know it was iron 2 plus, Mr. Dion? Because the other ion is a sulfate ion, and sulfate is always SO4 2 minus. So that means that the iron must be 2 plus. There's our iron 2 plus. Okay? And it's saying that we're starting with potassium permanganate. What's the permanganate ion? Well, you're like, I don't even know what a permanganate ion is. You should, because potassium is K plus, and permanganate is MnO4 minus 1. So there's our permanganate. So the ratio is 5 to 1 from our balanced equation. Okay, then we take the exact same strategy that we did in the last problem. Okay, for our concentration of iron 2 sulfate, we need the number of moles of iron 2 sulfate divided by the volume of iron 2 sulfate. Well, the good news is we already have the volume of iron 2 sulfate, 25 milliliters. So if you divide that by 1,000, you have 0.02500 liters. So then the question becomes, how do we figure out the number of moles of iron 2 sulfate? Look, we have the volume and the concentration of this, and we have a balanced equation. Let's do it. I gave myself more room down here. So we know that we have 0.01642 liters of KMNO4. Right, I just took this and converted it into liters, dividing by 1,000 in my head, multiplied by 0.1327 moles of KMNO4 in 1 liter of KMNO4. I know from my balanced equation that for every 1 mole of KMNO4, I consume 5 moles of iron 2 sulfate. Let me stop right there just for a second. We can work this out, okay, and we figure out that we have 0.01089 moles of iron 2 plus, okay, of iron 2 plus. And if you're like, well, where? I don't see any sulfates in here. I don't see any potassiums in this equation. Well, where's that? Right in this equation, okay? Spectator ions are left out. Okay? They're not even in there. Okay, we leave spectator ions out. Why? Because they're not affected by the reaction. Okay, and so we have the we have the number of moles of iron 2 plus. And if you're like, well, how did you go from iron sulfate? Oops, I don't know if you can see that. How did you go from iron sulfate to iron 2 plus? Well, remember, okay, back to oxidation numbers. If you have FeSO4, right? SO4, as I just told you, is always 2 minus, so that means that the Fe must be 2 plus. So again, we left out the sulfate ion because it's a spectator ion. There we go. We've got our concentration of iron 2 plus. Take that, copy it, and we'll paste it in here. And when we work that out, we get 0.4358 molar iron 2 sulfate. And if you're like, why are you doing it again? Why are you switching back from iron 2 plus? Because the iron 2 plus is in the iron 2 sulfate. Okay, that's why we can do that, and that's the final answer. Before we finish, I want to show you one more thing about this equation. Okay, I'm going to rewrite the whole entire equation here. So you have 5 iron 2 plus ions plus MnO4 minus plus H plus. 8H plus gives you Mn2 plus 5 iron 3 pluses plus 4 H2O. And I want to talk about this reaction just in terms of redox chemistry, okay? Oxidation and reduction. So if we think about this in terms of redox, what's being oxidized and what's being reduced? Well, remember, oil rig, that oxidation is losing electrons, and reduction is gaining electrons. Remember, electrons are negative, okay? Well, with that in mind, let's take a look at the iron 2 plus. The iron is going from iron 2 plus to iron 3 plus. Can somebody tell me, is the iron gaining or losing electrons in this reaction? It's losing electrons, right? If you're losing negative, you're becoming more positive, right? It ended up losing electrons. So it lost an electron, and so the iron 2 plus is being oxidized. This is oxidation, oxidation. Let's take a look. Can anybody tell me what they think is being reduced in here? It's not a trick question, but it might not be abundantly clear unless you really look at it really closely. Can anybody tell me what's being reduced? No, it's not oxygen. The charge or the oxidation number of the oxygen isn't changing. There's no magnesium in here. It's manganese, right? Mg is magnesium. Mn is manganese. Okay, it's the manganese that's being reduced. Let me prove it to you. If we evaluate the oxidation number of the manganese, it's going from something to 2 plus. Well, let's unpackage the permanganate ion. MnO4 minus. What's the oxidation number of oxygen in permanganate, right? It's -2. If I have -2 and I have 4 of those, I have a total of -8 for all of my oxygens, but I want to end up with a charge of -1. So that means my manganese must have a charge of +7. So the manganese is actually +7, and it's going to 2 plus, right? So I can put here, oh wait, it's written here 7 plus. So it's going from 7 plus to 2 plus. So that means it's gaining electrons, right? It's gaining 5 electrons. So the manganese is being reduced, reduction. All right. Remember, you can't have oxidation without reduction. The oxygen didn't change, right? The oxygen was -2 here. It's -2 in water. The hydrogen is +1 here. It's +1 in water. I went over that with you earlier this evening. And there you go. That's a redox titration. Give me a thumbs up if you're like, just lock me in a room maybe for an hour and I'll practice it and get the hang of it. Yeah, that's usually what it takes. It takes some time for all students to sit down with the problems and evaluate them and give them a try. I found that lecturing on titration, it's one of those concepts where I can sit here and talk to you about it for hours and hours and hours. But until you actually sit down and stare at it and try to figure out what's going on and understand the concept of neutralization, having a balanced equation, being able to figure out the number of moles of B from the number of moles of A, and then plugging that back into a formula to get the concentration of an unknown.